everybody, my name is Miwa Yokokawa, and I'd like to talk about sorting as observing experiments and strata. Before I begin my talk, I'd like to express my appreciation for Astrid and Rika for inviting me to this workshop. And it's very nice and I learned a lot. And I'd also like to express my appreciation to Gary to help me a lot in various aspects. So, my talk is about this title, and I'm a sedimentologist and doing an experiment for bed forms to get the information applicable to the ancient rock record. We use the grain size and shape sorting to interpret ancient deposits and the flows that created them. So I will show you some examples here. Left-hand side is modern river flat deposit, and the right-hand side is deposit from gravity currents, which is almost 100 million years old. You can see some structure inside the strata. A trained sedimentologist knows that these deposits were impressed by some kind of bed forms. The sedimentary structures inside the strata are described as laminations, lamini, or bedding, or stratification. These are records of bed form migration. For the upper left-hand side slide, planar lamination was impressed by plain bed, and the cross lamini above were impressed by ripples. And we know the formative conditions of these bed forms as the right-hand side figures, and from previous fluid experiments, so that we can interpret this strata as deposition from plain bed to ripples, in other words, waning flat flows. For the lower left-hand side, we can see antediluvian cross lamini in the lowermost part, and planar lamini above, and the cross lamini uppermost part of the sandstone. So that we can interpret this is deposition from decelerating gravity current. Now, to identify these sedimentary structures, we need different sizes, densities, and shapes of grains. And sorting mechanisms are key to identify these structures. And what if the grain size distribution is uniform everywhere, and there is no obvious internal structure? How was the deposit made? Can you guess? There are big arguments among us about reconstruction of the paleohydraulic conditions. The former slide is this part. And I'm sorry. This is a massive structureless deep sea turbidite. And we look at the surrounding deposit, and where we can see sorting and interpret this is the deposition from the turbidite currents. So now you see how important the grain size and shape sorting for us. And now we are trying to apply the morphodynamics models to estimate the ancient paleo flow conditions. And we need models which are applicable to mixed size sediments, and we need to include the key sorting mechanisms. So this is a table of contents of this talk. I will introduce first fluvial deposits as an example of strata for use, and then talk about the sorting with bed forms. So there are several kinds of river channels, such as braided channels and meandering channels, but today I don't have enough time to talk about all of them, so that I will use meandering rivers as an example. As you know well, a meandering river consists of channel, point bars, and floodplain, levees, oxbow lakes, and crevasse sprays. So what kind of strata are deposited by meandering rivers? So these are the features of the positional model for meandering channels. The deposition of meandering channels are characterized by this kind of upward falling stack of strata. The lowermost part is basal rock deposit, which is correlated to the channel floor. Above the base, point bar deposits consist of large packets of showing trough cross stratification and packets of pile lamination, and these are deposits of dunes migrating on the point bar, like this diagram. Above that, there are smaller cross stratification, which is deposits of ripples on the shallower part of the point bar. The uppermost part is mud, which is the deposit of floodplain. Please note that this fining upward pattern is formed by lateral accretion of point bar. So the vertical stacking fining pattern of the strata does not represent the vertical distribution of the deposit location, but instead horizontal distribution of the various morphologies. Now I will show you an example of the outcrop of meandering river deposit. The upper panel is a photograph of the outcrop of river deposit from about 70 kilo-years ago, when the river flowed into the parallel Tokyo Bay. The lower panel is a line drawing of the photograph. And you can see this is the abandoned channel, and these are the point bar deposits. I will show you the close-up photograph of this point bar deposit next. So these are close-up photographs of the outcrop in the former slide. And you can see the sedimentary structure in the strata. You can see these kind of structures here, and they're here. Here also, these are called trough cross lamination, and here some plana laminate, and these are called plana lamination. And all these are deposit of dunes on the point bar. And sedimentary structures such as laminations and stratification are the record of bedform migration. And each bedform leaves characteristic sedimentary structures corresponding to their shape, migration rate, and sedimentation rate. And we can reconstruct bedforms from strata using these sedimentary structures. If you can see only this part, we know what kind of bedforms migrate at that time. So, and we can reconstruct the waveforms from this strata, and we can also estimate the barrier flow conditions from them. So for example, these are dunes visible at low tide in Solomon River, Bay of Fundy, Canada. You can see the dunes left by the air current. If you cut the dune vertically parallel to the flow, you will find this kind of structure inside the dune. And this is the footprint of faucet migration, faucet of dune migrated. And why can we identify these structures? So identification of, to identify the lamni, you need different sizes, shapes, and density of grains. Otherwise, you cannot see the nation. So, and left-hand side, this is the microscope image of a thin section of faucet of dune generated in the blue shown on the right-hand side. Right-hand side. This is a big room, 4 meter wide and 160 meter long at Tsukuba University. And in the left-hand side slide, you can identify the faucet lamni by the alignment of small black magnetite grains. So you see these small magnetite grains. These densities are almost 5 grams per cubic centimeters, and these large ones are volcanic rock fragments, and these white things are quartz, and all these are like larger and 2.2 or 2.3 grams per cubic centimeter. So light and so small, denser, heavier magnetite and lighter, bigger grains are deposited separately and make the lamni identical. So in lower flow regime for ripples and dunes, lamination is the result of these three phenomena. And first is horizontal sorting during the movement of grains, and second is sorting associated with grain flow, and third, sorting associated with flow separation at the top of the faucet. The photo on the left-hand side here, here. This photograph was taken at the initiation of ripples, and you can see through the water, above the water, that the black heavy minerals organize into groups. This is partly because heavy minerals and light minerals move with different velocity. This is a horizontal sorting. And right-hand side is a schematic diagram showing the sorting effect at the faucet surface. Grains moves on the store side of ripples, and here flow separation occur, and some light small grains captured by the separated flows and jumped out from the faucet and falling down on the faucet surface. And the other larger grains going down as a grain flow on the faucet surface. And I will show you the movie of migration of Gilbert delta here. The yellow or brown sand is 0.2 millimeter, and the blue colored sand is 0.6. I'm not sure what happened, but okay. This keeps going. Right. So you can see the avalanches occur on the faucet, so causing grain flows that cause sorting, as the former presentation. And at the top of the faucet, you can see the flow separation occur, and the final grains are captured by separated flow and jump out forward, and fall out on the faucet surface. And you can see this faucet lamina here.
So it looks like there's yellowish sand being thrown off the top, and there's also yellowish sand kind of cascading down the surface in a granular sort of flow. Do you have a sense, because it's hard to tell from the movies, is there a sufficient size range of the sand that is the finer of the yellow sand that's going off the top, is the coarser of the yellow sand?
Yes.
Is that what's going on?
Yes.
Oh, okay, thank you.
So here is some natural examples, and upper photo is ripples at the upper part of the point bar, and lower photo is the vertical section of these ripples. I hope you can see these faucet lamina. I just put some guidelines. And this is an example of dunes, and again you can see, so this is the vertical section, and these are close up of this part, and you can see this faucet lamina here. So now maybe you see how you see faucet lamina is how those faucet lamina are formed by the migration of ripples and dunes. And so the next, let's think about the case of upper flow regime wet forms such as antidunes and cyclic slips, which do not have a faucet surface. And this is a photograph of flooding of Joganji River, and 3D waves occur on the water surface, indicating the existence of 3D antidunes beneath the water. And first I will explain what kinds of sedimentary structures will be left by antidunes. And this is these left-hand side are the snapshots of a flume experiment. And 3D surface waves and antidunes are formed by following process. The first 2D antidunes are formed, like A here,